All right, hi everybody. My name is Lendacky. I work at AMD in the Linux support organization, and where we provide kernel support for new AMD processor features. One of those features that is going to be coming out is memory encryption, and so that's what I'm going to talk to you today about. I'm going to talk a little bit about the host memory encryption, along with mostly the Secure Encrypted Virtualization, the virtualization support. So the first thing I'll do is I'll take you through the technology behind this. I'll talk about the key management, the encryption keys that are used to do this encryption of the guests and the host or hypervisor. And then I'll talk about what the integration, or what we think we need for integration into KVM and the tool stack in order to get this all together and working. So the main motivation behind this is really kind of a cloud environment, right? You have a lot of VMs that are running, the co-resident, and you want to make sure that one VM isn't going to be able to affect another VM or get data from the other VM. So there's a lot of things that you have to trust your hypervisor to do, right? The hypervisor has to enforce all the isolation between those VMs. And it's typically done using hardware virtualization, right? Logical isolation with page tables, VM intercepts, and things like that. But as we've seen in talks earlier today, things can go wrong, right? And you can end up with things breaking down. So your cloud users really have to trust the cloud company, right? The cloud company's really got to provide that full isolation so that it can protect all of the secrets that a guest may have, and so that's not ideal for both users and cloud companies. So some of the attacks that we're trying to defend with the memory encryption, with the secure memory encryption, we're trying to protect against physical attacks. Right, so somebody who has physical access to the machine and can do things like probe the DRAM interface, and we've even heard this, freeze the DRAM and take it and be able to access it later. Right, with NVDIMMs coming out, that's going to make it even easier to be able to physically get to some data. The Secure Encrypted Virtualization kind of works more against user attacks, right? So we want to prevent administrators from being able to go in and just look through guest memory, right? Or just the hypervisor bugs that allow a hosted guest to steal the data from another hosted guest. So these are the types of attacks that we're trying to defend with this memory encryption. So just an overview of how this works. It's a hardware AES engine that's in the memory controller and performs inline encryption or decryption as data passes through. There's minimal impact. There's extra latency only if the page is encrypted. We're working on measuring that, and so hopefully in the future we'll have some numbers to show the performance impact associated with that. And the real goal was to really have no application changes, right? Let's try and keep all the changes down in the OS so that applications don't need to be recompiled or changed or in any way are affected by this. All the encryption keys are managed by the AMD secure processor that's running, and that is a processor that is hardware isolated from the x86 CPUs. So none of the keys that are in the memory controller can be accessed by the x86 side, right? And they're all just controlled and generated and managed by the secure processor. For the secure memory encryption, Again, it helps defend against physical attacks mainly, right? It's a single key that's used, and it will protect anything that's running within the OS. So even if you don't use SEV, you can protect VMs through the host memory encryption. If you have containers running or sandbox VMs with other containers, you can protect those. The OS or the hypervisor decides what it wants to encrypt. So there's an encryption bit in the page tables. I call it the C bit. And that is used to determine what is going to be read as encrypted or decrypted. And it starts up at the CR3 register. So if the CR3 register has the encryption bit set, then the PGD table will be read as if it was encrypted. It would be decrypted, and that proceeds on down until the final entry to get to the page data that you're trying to access. And if the bit is set, it'll be accessed as encrypted. If it's not set, it'll be accessed as plain text. There's support for hardware devices to be able to DMA into and out of memory. So the device would need to support where the C bit is located. So that would be most likely it's going to be bit 48. So you need to have a device that can support 48-bit DMA or higher. If you don't, then we would have to use bounce buffers in that case. So now Secure Encrypted Virtualization, what we do is we have the one key that we talked about for the hypervisor, but then each VM can have its own key, right? Or you can group VMs into a key by sharing that key or allowing sharing of that key. Or if you run sandboxes or lightweight VMs, and there was talk, I think, this morning that I heard about trying to get containers to come up faster through lightweight VMs, you'd be able to further protect containers in a VM environment. So what this does, it cryptographically isolates the VMs from each other. So if each VM has a different key, one VM will not be able to read the data of another VM should it happen to break out and try and access it, right? It would just kind of appear as junk. And since it wouldn't have access to any of the keys, it wouldn't be able to try and figure out what's going on. So this all integrates with the existing AMD virtualization technology. And I say you can also run unsecure VMs, but I mean, you can just run non-SEV VMs. I don't want to say everything's unsecure. This is kind of a pictorial overview of how this looks. The guest owner communicates with the hypervisor to indicate whether he's going to want an SEV guest. And the SEV driver that we're also developing will communicate with the secure processor. The secure processor will generate and manage all of the keys. Once the keys are loaded, at that point, any accesses, through the memory controller are then going to be either encrypted or decrypted, and any accesses where that C bit isn't set would just pass through as normal. All right. So from an SEV point of view, how do we do this? The VMCBs that we have an address space ID associated with the guest. Currently, most of the SEV or the ASIDs, we just keep incrementing in KVM today. What we're going to have to do is have the ACID associated with all vCPUs of the guest. The ACID is tagged with all the data that's in the SoC, so cache lines, TLBs, that kind of thing. And the ACID determines the encryption key. So what we'll do is associate the ACID with the guest, with the secure processor, and load the appropriate key and access the data that way. With SEV, there's certain things that are a little different than SME mode or that host mode, right? Any instruction fetch is always going to be decrypted. That prevents anybody from trying to inject code into the guest. Okay, guest page tables are always encrypted, or I've been using the term private here. So anytime a page table walk is done, it's always done through decryption, so that the hypervisor can't try to change any of the page tables out from underneath the guest. All right. Data pages can be marked either as shared or private, or encrypted or non-encrypted, right, depending on what the guest wants to do. And before any of the paging is active, and before the PAE is set, all pages are private. So if you're running in real mode, it's all accesses to memory are going to be decrypted, whether it's instruction fetch, reads, anything like that. The only exception is that, so all DMA has to be done to shared pages.
How does that work for a bootloader?
So I'll get to that in a little bit. So, so I'm going to talk a little bit about key management, okay? And this is, I probably need a lot more time to really go into everything behind the API that we have and how everything is done. So this is going to be a real quick overview for key management, and we can talk afterwards if anybody wants to know further details. But we're trying to make sure we fit the full VM lifecycle, and it all starts with platform authentication, making sure that we can bring up guests, do migrations or snapshots of those guests, and take them all the way through. The key management is all done by the secure processor in firmware that's running over there. All right, so everything is isolated from the x86 processor. Right, and we communicate with that secure processor through a driver and through mailbox registers and shared buffers. Okay. The purpose of the secure processor is to help with the VM lifecycle, right? And so it generates and manages the encryption keys, as I stated before. It does some bootstrap memory encryption during a guest launch, right? So that's how we would launch a guest right from the beginning if it's running in, say, real mode. So BIOSes, things like that, we would have to tell the secure processor to pre-encrypt that or encrypt that before we actually start the vCPUs, right? That could be done either as a guest that has been transmitted to the cloud user in, say, a protected wrapped transport key, or just a plain kernel NIDRD BIOS kind of thing where we point to that, the secure processor will encrypt it based on the key that it has allocated for that guest, and then at that point we can start the vCPUs. The same thing kind of goes for migration and snapshots, and we're still looking at how it's going to be best to do this. But when we do migrations now, we're going to have to take the pages and take them through the PSP or secure processor. I'll call it PSP too, kind of a historical name for it. And we'll have to decrypt those and wrap those in a transport key and then send those on. So it'll be a little more difficult and a little more work that we'll have to go through, and we really need to take a look at how we're going to be able to best do that. And the other thing that the secure processor does is we have guest policy associated with each VM, right? So the guest policy has things like whether or not to allow debug access, right? So if you're trying to see what's going on in your guest because it's not booting all the way right, you want to be able to maybe do some debugging before making everything final. So we have the ability to do that through debug, encryption, and decryption APIs. Some of the other policy is whether or not the guest is allowing its key to be shared. so that if you want to group multiple VMs into, say, one key combination, you can do that. So, maybe a company runs all its guests under one key. And part of this whole guest life cycle, right, we have to take it through the platform key and certificate management. And the platform key kind of shows that we're running on a true AMD platform with SEV support. The certificate is going to be used with the cloud provider, and so all of that kind of comes together to provide authenticity of the platform and ownership of the platform, so that when we do all of the encrypting, the initial encrypting, we can prove that what we're running with is what we meant to run with, right? So it's one thing to just have a guest that's running in encrypted memory, but how do you know it's the guest that you really wanted started, right? And some of the stuff that I'm kind of leaving out a little is the fact that every time we have the PSP do some of that bootstrap encryption, it's also measuring all of that data and then signing it and providing a measurement back that can be used to validate and verify that everything is as it should be. So I talked to these a little bit already, but launching, right, the guest image is created and with unencrypted components or with wrapped encrypted components, right? And we need to bootstrap that encryption in order for the guest to run. Migration and snapshot support and activation. And activation is the ability to associate that ASID that we have for the guest with the memory encryption key that's in the memory controller, right? And so we have a certain number of key slots, so it allows that way for overcommitting of key slots. So integration.
Quick question. Are these encryption keys valid after SVS4?
What's that? Are they?
You mentioned that the encryption keys, right? Are they valid after SVS4?
Well, so you need to be able to maintain for the host, say the SME case. If you do an S3 or S4, right, we do save off that key so that when it comes back, you're going to be able to continue running properly, right? But otherwise, per boot, the keys will be kind of refreshed or repopulated through the RNG that's in the secure processor.
So keys are kind of visible to software?
No. So the keys are only visible to the secure processor, and so when you do an S3 on, say, the whole machine as opposed to a virtual machine, on the bare metal machine, right, it will save off that key in SPI flash, and it will wrap it so that it's out there encrypted, it's not in the clear.
The security processor will send the keys into the processor.
Right. Right, and the idea for VMs, when you try and do like a save restore kind of thing for VMs, right? That same type of thing would happen, but not necessarily at like the machine level, right? We'll have to make sure we get a wrapped version of that key. And save that along with the saved data, and then when it's time to restore, that will be processed and by the secure processor, unwrapped and put back into the slot. So we submitted some RFC patches recently. Brajesh, my coworker, submitted those recently, and some of the things and some of the areas that we updated or worked on in order to provide this support and support the key management API. So we have a new iOctal and KVM so that we can launch guests or migrate guests, right? So we'll be able to unwrap and encrypt guests and get them ready for execution. Wrap and unwrap guest pages for migration, and we'll also have a driver that will that we're supplying so that we can do the communication to the secure processor. Updates the virtualization code. We have some patches that are probably going out fairly soon on what we've done to QEMU in order to try and run this and get this get the key material down, initialize the platform and things like that. But there are going to be we're going to need to do updates to things like libvirt and tools up the stack in order to integrate this and get this all working. Right. I mentioned this a little bit, ACID management. So right now, SEV guests are going to have the same ACID for all vCPUs. All right, that's a change from the way things currently are, and it's going to require a TLB flush if we run a different vCPU from the same guest on the same CPU where we just ran a different vCPU. Or if we take a vCPU and run it and take it from one CPU to another CPU, we're going to also have to flush there so that we make sure that we get everything straight. There's going to be a certain range of those ACID values that a guest is going to have, an SEV guest will have to have in order to run as an SEV guest. And non-SEV guests can still use any ACID, and it can actually use some of the same SEV ACID values, but we would rather not do that so that you don't remove any SEV resources. I mentioned this a little bit, debug support, right? So that's going to be controlled through guest policy, and it'll allow for QEMU to encrypt and decrypt the guest memory so that it can continue to maintain compatibility with the way the QEMU debug support works today. Paravert drivers, so this is going to be one of the more interesting things. So any kind of driver any paravert driver that's going to need to have the memory shared between the host and the guest is going to have to be marked as unencrypted, right? So VirtIO, we're going to have to make sure that the virt queues and any buffers that are used are marked unencrypted. The KVM clock is an interesting one because that's very, very early in the boot, so we're going to have to figure out how to go about making sure that we mark the page the KVM clock is using as unencrypted. And any other paravert drivers that are out there, we're going to have to look and see and make sure that we do everything in a shared fashion so that the communication can continue. DMA in the guest currently must be performed to shared pages, right? So we're going to have to make use of the software IOTLB to go between all the private and shared pages. So a little bit of bounce buffering going on there. But that's kind of where it is for this first generation of this support. So a quick summary of what we're doing, right? So the secure processor firmware that we're developing, it's going to be doing all the key management work. It's going to be signed by us, so it's cryptographically signed so that we know that we have valid firmware. And that is not open source. But the Linux driver that we're going to be using to talk to the secure processor, that will be open source, and any of the major work that we're doing out in the kernel and KVM and QEMU, that's also going to be open source, obviously. And we have some patches that have already been submitted, and hopefully we'll be getting some feedback on those soon. There's some references here, some white papers and some specifications, and in particular the API specification is out there, so you can see the kind of APIs that are there to provide kind of that attestation of a guest as it boots up. And that's pretty much all I have. I've got 5 minutes left for any questions.
So not sure if I understood it correctly, but I can decrypt pages from my hypervisor.
You can decrypt pages.
So if I'm in the hypervisor, I can decrypt pages of my guest because I need it for migration purposes, other kinds of stuff.
You can't do it directly. You would have to make a call into the secure processor, and it would decrypt it and wrap it. So the only thing that you would see is now an encrypted version that would be used for transport. So you wouldn't be able to see any plain text data.
Where's the other key coming from then?
The other key would be part of the guest owner that creates this transport key. So there's, this is why I kind of needed more than 30 minutes to cover some of this. And we can maybe talk about it in the Birds of a Feather session. But the guest owner is going to have to supply some key material, and one of those is going to be a transport key that can be used for migrating pages, right?
Okay, so in short, if I can escape in my hypervisor, I won't be able to read any other guest memory.
Right, you won't be able to, you'll be able to read it, but it'll look like garbage, right?
Okay, and the other thing I was wondering about was nested virtualization support.
So for the nested virtualization support, and I'll have to double check on this, but I think we're going to have to run one level.
I think it will be problematic.
It might be. I think we might have to do one level without, right? So I need to double check.
I mean, this is especially relevant then when running containers in such a VM, because these containers can just start other containers, and then you have to like make a point which kind of security you want at which level. So.
Yeah, I mean, it depends on how everything is organized, right, as to where you put that encryption support.
Hey there. So the untrusted hypervisor, let's assume that's not an oxymoron. The untrusted hypervisor can't read on a whim any guest memory, and you've explained how kind of that would work with live migration. But as a matter of course, KVM does instruction emulation, and it reads guest memory to decode the instruction. But you said that all guest instructions are encrypted. So how does that?
So the only time that we need to really read guest instructions, right? So there's support for MMIO accesses where we actually get we can avoid guest page table walks because we get the actual guest physical in the CR2 register, the guest CR2 register. And we've unrolled, the only time that we would really need to crack the instruction is on like a string IO operation. And there's not very many of those in the kernel. I think in the patches that were sent up actually unroll those to just do ins and outs. And so that doesn't need to be.
Sorry, in the guest kernel.
Yeah, well, in the kernel in general. Yeah, the guest kernel.
This seems to fly in the face of, say, the second talk that we heard, which was about taking the 4% of KVM, which is the instruction emulator, out of the kernel. So I still don't understand.
We don't need to emulate any of the instructions that isn't supplied in the exit information. So we have all the information when we exit that we would need to do.
There's not enough information. You need the page tables. You still need the page tables.
No, they have added all the stuff that's needed.
Oh, okay.
In MCP.
So on the exit, you deliver the instruction.
Right.
So during migration, you can call the secure processor to cross-crypt, whatever you want, transcript your pages. But how do you know which pages need that? Because the crypt bit is in the page tables, which means it's indexed by virtual address. But when you're migrating, you're going by guest physical address.
So the thing that's interesting is that we're gonna have to figure out some ways, right? Because the guest as it is now, like QEMU when it's doing migration is just looking at the nested page tables, right? Or not the nested
it's not
page
even
tables.
looking
I
at
mean,
it,
the
just-
guest,
it
the
looks
guest,
at
the
guest
guest
memory.
memory,
Yeah.
right? It's just walking the guest memory, and a lot of times it's looking for 0 pages, which it's not going to see as 0 pages anymore, right? So we're going to have to, we either are going to have to just transfer everything, right? But everything will be, encrypted in the guest, so that when we do call the secure processor, it's.
But my point is that if you're looking at a guest page, like 4096 bytes of data, you can't tell if that's encrypted or not if you don't have the key.
Yeah, let me think about that a little bit. I know we've talked about this and stepped through it, but I'll need to.
The other question I had is,
One question, do you update the IV for the encryption to, for example, avoid replay attacks, so that you basically save an old memory copy and replay that old copy later on to force the guest into doing something strange?
So the algorithm that's used doesn't use an IV. It's basically an AES ECB with a tweak, right? So that kind of helps prevent any kind of replay attack, and also so the advantage of that is any page, if you were to just take a page and move it, it won't decrypt properly, right? So it's actually got to be decrypted by the PSP or the secure processor and then re-encrypted in the new location. Any other questions? All right. Thank you.